Hello everyone, welcome back to another algebra video. In this video we're going to be solving problem 3 from the fall 2023 algebra qualifying exam at UC Irvine. The exam is not posted online yet, but as soon as it's posted online I'll provide a link to it in the description below. So problem 3 is saying let R be a non-zero finite commutative ring with unity. Prove that every prime ideal in R is maximal. So just thinking about this kind of problem, kind of imagining we're solving this on a test, first thing that came to mind when I read this problem is kind of the phrase, finite integral domains are fields. So of course, this popped into my head when I read the problem. No guarantee that it's going to provide an easy solution. Sometimes you think of things and it just doesn't work out nicely. Lucky for us though, this kind of is the way to go, or at least one way to go. And I'll show the proof of this statement at the end, but let's see how we can solve this problem just using this fact. So kind of thing to keep in mind, finite integral domains are fields. So okay, we have a ring R with these conditions. Prove every prime ideal in R is maximal. So let's do it. Proof. Let P a prime ideal in R. Then R mod P is an integral domain. And maybe one thing I'll point out here, so this is using the fact that if I take a ring mod out by a prime ideal, I get an integral domain. Why did they tell us R is non-zero? Well, it's because we only define integral domains for non-zero rings, so that guarantees that R mod P is indeed an integral domain. So this is good. That's also, we only define these things for commutative rings, so okay, looking good so far. We also know R is finite though, so the quotient here is finite. So I'll say R mod P is also finite because R is. So again, now we use this fact, finite integral domains are fields. So I'll say by, let's call this star. So by star, R mod P is a field. But what do we know about kind of quotients that are fields? Well, it means that the ideal I modded out by had to be maximal. So this implies P is maximal. And that's the proof. So, that's the proof if, I don't provide a proof of star, but let's provide a proof of star just to cover our bases. So say proof of star. So, okay, let's start with a finite integral domain. So maybe I'll do it in red. Let R a finite integral domain. I'll abbreviate it as ID. Now, what I want to do is I basically need to show that all non-zero elements have a multiplicative inverse. So I'll say need to show if A in R is non-zero, there exists A inverse in R such that A inverse, which, this is commutative, so if it's a right inverse, it's also a left inverse. This is the identity for multiplication, so the unit. All right, so that's what we need to show. What I'll do is I'll say consider. So this is going to be for all A not equal to 0 in R, the map. So let's call it maybe phi sub A, which takes X, or maybe let's see, how do I want to do this? Well, let's see, so it takes R to itself, but let's say it takes little r and maps it to AR. And the claim here is that phi sub A is invertible, so it's a bijection, injection and surjection. Because R is finite, if I can prove just one of those things, then both hold. So let's see, my claim is that phi sub A is injective. So I will say, let's suppose phi sub a of b prime is equal to phi sub a of b double prime. Well, let's look at the map. This happens if and only if ab prime is equal to ab double prime. And just moving things, so this is ab prime minus ab double prime equal to 0. If and only if, let's factor out a times b prime minus b double prime is equal to 0. Now this is where we're going to use the fact that we're dealing with an integral domain. So R in integral domain implies that either a is equal to 0 or b minus b double prime is equal to 0. But a equal to 0 is impossible by assumption. So then what this means is that b prime is equal to b double prime. So this means phi sub a is injective. And because R is finite, this implies that phi sub a is also surjective. And hence bijection in this case. So in particular, we know the map is invertible, so there has to be an A inverse. There has to be some element of our ring where you multiply it with A and you get the identity. We showed that this holds for all A non-zero in R. So in particular, if A is non-zero, so kind of therefore, if A is not equal to 0, there exists A inverse in R such that A inverse is equal to 1. So that's the proof if we have a finite integral domain. Well, it has to be a field, right? What's the difference between integral domains and fields? It's kind of this existence of multiplicative inverses. So, all right, pretty quick and straightforward problem. Let me know if there's any questions in the chat. Thank you so much for watching, and I'll be making more of these videos for this exam.